On our previous video, not only did we look at how sine was able to meet our odd symmetry based on its origin as shown right here for the equivalence of their translations, but also this was applicable to the tan function in respect to its translations as they are equal to each other in terms of how they meet the odd symmetry origin criteria. Now, in this particular video, we're going to explore cosine and how it is indeed an even symmetry based on the angle and what makes it to be rightly even, as well as not only proving it through the graph, but most importantly by imputing angles to see what equivalences of its translations rightly matches its even characteristics. So let's begin. Now, focusing on cosine, what we see is that when you graph the original function of cosine, where on our y-axis is cos theta and our x-axis represents our angle, we're going to divide this into quadrants where moving from our origin, which is located right here, to the specific right side of the origin, we have this to be pi over 2 and next is pi, and moving from our origin to the left we have this to be negative pi over 2 and we have this to be pi, and we can include this to be negative 3 pi over 2. Please don't forget your negative sign right there. So now what we recognize is that when we are at 0, in this case cos theta, in this case cos 0, this gives you a value which is 1, and 1 is where we're going to begin on our y-axis, and we're going to move what way? Down to the right. And what we recognize is that from our 1 value we're going to make this strip around to our pi over 2, which is in this case equal to 0 for the cos of the angle, and then to pi cos of pi, which is equal to negative 1, and then back to 3 pi over 2, which for cos of that gives you what? 0. And likewise when we do it the other way from right to left from our origin, we actually head to our 0 mark for our negative pi over 2, and then all the way to negative 1 for our negative pi, and then back to 0 at this particular angle, negative 3 pi over 2, and so on. And this shows some interesting behavior in terms of recognizing the following. We recognize now that when we want to prove that it is an even function, we recognize that there are 2 equivalences in terms of the specific translations, and what it is proven is that our cos theta, which is what we graphed right here, is equal to the graph cos negative theta. We can prove this by constructing the graph of cos negative theta and see how it matches or is compared to this particular original graph that is made, and this is how it is done. And now we're going to begin with our angle first to be equal to 0, and what is going to be the result where you apply your cos negative theta to the theta equal to 0. And what that gives us is that our cos of 0 is equal to what? Is indeed equal to 1. And so what that looks like is that we're going to have our first point, which is 0, 1, and this is going to be placed right here. Now the next one is where your theta is equal to pi over 2, and you're applying it to your cos of our negative theta. What does that look like? It means that our cos of negative pi over 2 is equal to what? It is equal to 0, because our cos pi over 2 equals to 0. If you perform the negative pi over 2, we are going to get our 0 to be produced right there. So for this, it is going to be placed right over there. Next is theta equals to pi, and what that looks like when you apply your cos negative theta to the angle is that our cos is going to be applied to negative pi, and this gives us what? -1, and this is going to be placed the point right here for our pi and -1 point. And therefore we are going to be doing the opposite side. We see that we have our cos of, in this case, -pi/2, and this here theta equals to -pi/2. This here is going to be applied, our cos is going to be applied to the negative of our -pi/2, which gives us what? Cos +pi/2, and we know that cos +pi/2 is equal to what? It's equal to 0. And so what that implies is that where our angle is at pi/2, our cos of the angle is equal to 0, which is placed right there. And you can try this for yourself. We should see that our cos of pi, because of the negative signs cancelling out, remember that there is a negative sign right here, this is going to be translated on the point to be right over there. Therefore, when you join your point, it should look something like this in terms of that smooth curve, which is exactly what we have right over here for, in this case, our cos theta. Therefore, this implies that there is a symmetry that is even, and this symmetry, it is along where? It is along the y-axis. And why is that the case? Let's take, for example, we have a specific angle that we want to check out, which is, in this case, we are going to try our angle pi/3. It will, when you do the cos of -pi/3, it will give you the same value as when you perform cos pi/3. And what we have is as follows. This here is measured to be what? 1/2. And when you do the same thing as well for your -pi/3, you should have the same value as what we had over there. So your result of your y is the same, either it is the positive of that angle or the negative of that same angle for cosine. Therefore, it is even because there is a symmetry along the y-axis. So I hope you found this really informative. Please hit a comment down below. Let me hear your thought about this particular short video about cosine and how it is indeed an even function based on the angles as it shows the symmetry along the y-axis. And see you all on the next one. It's all the same, stay smart as always and believe in yourselves.